Good morning, everyone. Myself Gautam Salma, and I welcome you all in a Sapience education. So today I am going to discuss about the chapter 1 of class 12, electric charges and field. That is the part 3 video. I have done so many topics in previous two parts. So let us discuss about charge distribution, Gauss law, and electric field due to dipole. Okay. So let us go for the charge distribution. See here, if we talk about the continuous charge distribution of the charge. Let us consider a linear charge distribution. First topic will be linear charge distribution. So suppose there is a wire of a length L, okay, and the total charge on this wire, suppose the total charge on this wire is let us consider is Q. See, this is the wire of a length L and the total charge in this wire is Q. Then if you want to find the charge density, that is charge per unit length, which is also known as linear charge density. So the linear charge density lambda can be written as total charge by unit length, so that we will get the charge density. Okay, so this is the method to find the density. Now we will go for the surface density. So let us consider this is the surface. This is our surface. Okay, and this surface has having a area of a, and there is an equal distribution of charges on the whole surface. And let us consider there is total charge Q and the area is A. So if we tell it as a surface charge density, if it is surface charge density, so surface charge density will be equal to total amount of charge on this surface divided by the area of the surface where the charge is being distributed, right? So I hope you have understood this. So this is surface charge distribution. Now let us go for a volumetric charge distribution. So volumetric charge distribution means what? See, let us consider there is a sphere, okay, and a whole solid sphere, and the charge is being distributed all over the surface inside the surface. So if total amount of charge is Q, so charge per unit volume will be known as volumetric charge distribution and volumetric charge density. Okay, so what we have learned? We have learned linear charge density, that is lambda. This is equal to charge Q per unit length, that is Coulomb per meter. We have also learned areal charge density or surface charge density, that is charge per unit area. So this will be Coulomb per meter square. And we have also learned about volumetric charge density. So this is also known as charge by volume. So that is equal to Coulomb by per meter cube. So I hope you have understood this three term, right? So let us go for next one. This was the basic. Now you have, I think, heard in this class 11 area vector. Area vector is what? The direction of the area. We generally take the direction of the area as the line perpendicular to this direction. So let us consider this is an area. So what is the direction of this area? So the direction of this area will be equal to in this cap. N cap is in this direction, right? Got it? Understood or not? Okay. Now by convention, the vector associated with the every area element. By convention, the vector associated with the every area element of a closed surface is taken to be in the direction of the outward normal. See, always take outward normal. If suppose there is an area, this is an area, and I want to know the what is the direction of this area, so we have to make a perpendicular vector in this direction, is that is n vector. Okay, and the area, suppose this is your del s, so the area vector can be written as delta s into n cap. So n cap will always try to give the direction which is perpendicular to that surface. So I hope you have understood this, because everywhere if you want to find the direction of the area, so what you have to do, you have to take a normal on that area, any type of area. Suppose this is an area, right? So you are seeing, so you want to find the direction of this area, so this will be the direction of the area. So del x is the magnitude of the area, del s, n cap is the unit vector outward normal at that point. So I hope you have understood the area vector, right? Now let us go for next electric flux. Electric flux, see, very important. Electric flux, it is a measure of the flow of electric field through a surface. It is equal to the product of the area element and the perpendicular component electric field integrated with the surface for the open surface. Let us consider this is the area and there is another area I'm drawing here. Okay, so try to understand here. Now the field lines, how many? 1, 2, 3 field lines are passing, and here I am telling you that the more than 10 field lines are passing. We can say that the flux, the number of field lines, electric field lines passing per unit area in a area is the measure of the electric flux. So here the flux is high and here the flux is less. So flux can be written like this. Flux is equal to E dot A for the plane surface. So flux phi is equal to integration of E dot del S. Flux is equal to integration of E dot del S. Okay. So see here, you have understood now, right? So actually what happens, electric flux can be written as electric field dot area for the plane surface and flux for the non-uniform surface. We can need to integrate because we don't know where is the, what is the magnitude of the electric field at each different surface. So this is very important formula, right? Now for closed surface, if there is a closed surface like this, so by definition, flux can be written as integration of E dot ds by definition, right? So now let us go for the Gauss law. So it is very important law. I hope you have heard this first time, Gauss law. So this is very important formula. Why? Because it has a huge application. You can find electric field within a one or two step by this law. Okay. So the total flux linked with the closed surface is 1 by epsilon naught times the charge enclosed by the closed surface. What do you mean by this? See, if you consider any of the closed surface, it may be this, it may be this, it may be this. Okay. So as per this, you know that everywhere if there is a charge, so there will be an electric field, and if there will be an electric field line passing through the surface, it means that what? It means that there is a flux present on it, right? See, in this way there is a presence of a flux. Every surface there will be a presence of a flux because every surface there will be an electric field lines passing through it, right? Now as per this Gauss law, if the surface is closed like this, you don't take a open surface like this, you can't take open surface like this. The surface should always remember it should be closed. So when a surface is closed, then the flux can be written as charge enclosed by epsilon naught. So charge enclosed means what? How much charge inside this closed surface is there? It may be 10 coulomb, 5 coulomb, whatever enclosed charge will be there. So charge enclosed by epsilon naught, this will be equal to the flux. And you know that flux has another formula we have already done, that E dot ds, integration of E dot ds. So this is very, very, very important formula. Now I always try to remember that this is applicable for only for closed surface. Don't forget while applying this. So this is the basic formula as well as basic principle of the Gauss law. Now, let us consider the important facts about the Gauss laws. Okay, see, Gauss law is valid only for the field which follows Coulomb's inverse square law. That is F is equal to K Q1 Q2 by R square. According to this, flux passing through the closed surface does not depend upon shapes, charge distribution or location of the charge. So it should not depend upon shape. If flux is changing due to shape, then it won't be applicable. It depends upon nature, value and medium of the charge, because you are using epsilon naught, because flux is equal to charge enclosed by epsilon naught. So epsilon naught is also dependent upon the nature of value and medium of the charge. Now net electric field associated with the closed surface placed on an electric field is zero if no charge inside the surface is there. Very important. If charge is not there, let us consider if there is a body but no charge is there, so flux inside this body will be zero, because no charge is there, so no electric field will be there. If no electric field will be there, so no charge will be there. So this is the fourth formula. I hope you have understood now. So we will go for a next slide and also try to find what is the application. See, so this is the part of application of the Gauss law. We can directly write this slide that this is an application of Gauss law. Application of Gauss law. Now, what is the first application? So, electric field due to special charge distribution. You want to find electric field. You want to find an electric field at a point which is at a distance of L or R or anything. So how you will find? See, now see here, I will give you one example so that you will understood well. Let us consider there is a wire having a charge positive, 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 okay? And due to this positive charge, I want an electric field at this point. So how you will find this electric field at this point? So basically what we will do, we will create a closed surface. So can we create a closed surface like this? Can we create a closed surface having a cylindrical shape and which will pass through this point P? So let us create a closed surface like this. It may be closed surface like this. So this is a closed surface. Got it? And in this closed surface, we have made a closed surface. Now in closed surface, we know that we can apply a Gauss law. So what is Gauss law? Gauss law is that flux in a closed surface is equal to charge enclosed by epsilon naught, right? Now here we have also learned about the flux. So flux will be equal to integration of E dot ds. Now tell me, total flux passing through this can be written as total flux passing through can be, how you can write? See, let us consider this is as a distance this r, okay, and this has how many surfaces? So this curved surface is one surface, this one is second surface, this one is third surface. So if we if we want to find flux on this three surface, that is flux on surface 1, that is E dot ds surface 1, plus flux at surface 2, that is E dot ds at a surface 2, plus flux at surface 3. So we want ds3 into surface 3, right? And this is the total charge enclosed, charge flux, and this can be written as charge enclosed by epsilon naught, right? So what we have to do here, we have to put the value. Now try to understand here, try to understand the direction of the electric field. See here, this is positive charge, so the direction of electric field is like this. Okay, no, this is not the direction of the electric field, sorry. This is the direction of wire. This is the direction of the electric field. See, this is the positive charge, so positive, so this is the direction of electric field. And what is the direction of the surface area? So let us consider this is the surface area, so the direction is perpendicular to the surface area, so this is like this. So here is 90 degree, so for surface 2 we have 90 degrees. Similarly, surface 3 has also the direction of the area vector and direction of electric field is 90 degree, right? So this is second one. Now third one, third surface area is your curved surface area. So in curved surface area, direction of electric field and the direction of surface, see, let us consider this is a surface, so both are in same direction. So for this, theta is equal to uh, for surface 3 theta is equal to 90 degree, for surface 2 theta is equal to 90 degree, and for surface 1 theta is equal to 0 degree. So all are dot product. So we can, what we can do here, what we can do, let us see here, integration of E dot ds one surface. So dot will be removed. Why? Because this will be E dot ds, means E dot ds cos 0 degree, plus integration of E ds 2 cos 90 degree, plus integration E ds 3 cos 90 degrees. So this will automatically get cancelled out, right? And this is equal to total charge enclosed by epsilon naught. Now see here, E, since electric field is constant at this point, see here, every point you will get electric field as a constant, so electric field will come out. So integration of ds is equal to charge enclosed. So how much charge is enclosed? See here, let us consider lambda is the charge density and the length of the wire is L. So the charge density lambda is equal to what? Charge by lambda is equal to what? Charge by length. So charge can be written as lambda, that is charge density into L. So we can write here charge enclosed is equal to Q enclosed, that is equal to by epsilon naught, that is equal to lambda L by epsilon naught. Now the question is that what is the integration of the surface ds? Since it is curved surface, so what is the formula for the total curved surface of the cylinder? So the curved surface of the cylinder, that is equal to E into 2 pi r. The r is the distance at this point into L, and this is equal to lambda L by epsilon naught. Now L got cancelled out. So from here, electric field E is equal to lambda by 2 pi r into epsilon naught. So you have got the electric field at this point R, at this point P, which is at a distance of r from the line charge density. So I hope you have understood this. So I have done all the things same here. You can see here, you can understand that how I have done this. Okay, see, again I can explain you. See here, there is surface 1, there is surface 2, there is surface 3. Now at surface 2, the direction of area is this and the direction of electric field is this, so the theta is 90 degree. At surface 3 also theta is 90 degree. But what about the surface 1? Surface 1 is curved surface, so curved surface has the electric field direction is in this direction and the area is also in this direction. So the theta will be equal to 0. So if theta will be equal to 0, so the term where theta will be 0, their dot product will not be 0, right? So here surface 2, surface 3 will automatically get 0 because the angle is 0. Now the surface 1. So for surface 1, total surface area is equal to 2 pi RL, and this is equal to charge enclosed by epsilon naught. Again, you know that how to find the charge enclosed. See, first of all, you need to understand that how much amount of charge is there, right? So total charge Q is equal to lambda into L. So here we have put lambda L. So where we got electric field. Now it is very simple to derive electric field at a point, right? So this is the application of the Gauss law. Now let us go for the another application. This is the application, a conducting hollow sphere, okay, and we want a electric field P outside the sphere. So let us consider here. I will teach you with the red mark here. See here, this is the sphere having a charge q, so total charge on the sphere is q, right? And I want the electric field at a distance of r, which is at a point P. Electric field at a point P, which is at a distance of r from the center. So how you will find? So I can make my imaginary Gauss surface. So this is also known as Gaussian surface. This is also known as Gaussian surface. So when I have done imaginary Gaussian surface, so what will happen? So draw the Gaussian surface passing through the point P. Why I am taking Gaussian? Always I have taken Gaussian surface passing through the point P. Why? See here, we have also done Gaussian. This is also a closed loop and this is a Gaussian surface. Gaussian surface means what? Closed surface. So I have by my own made a closed surface. So when I make a closed surface, so that surface is known as Gaussian surface. Now using Gaussian theorem, what we can do? So the integration of E dot ds is equal to charge enclosed by epsilon naught, right? Now what you will write here? E dot ds is equal to charge enclosed by epsilon naught. Now ds means what? Area. So the area of the circle having a radius r, area of the sphere having a sphere r is equal to 4 pi r square, and this is equal to charge by epsilon naught. Now you can easily find electric field at a point P, which is at a distance of r from the center, is equal to q by 4 pi epsilon naught into r square, right? So I hope you have understood this very well. Now let us go for a next electric field at a point A inside the sphere. See, let us consider there is a sphere, it has having a charge, and it is a hollow sphere, right? It is hollow sphere. You want to find electric field at a point P, which is at a distance of r from the center. Now how you will find? So the first and most important thing is that you have to draw the Gaussian surface like this. Now inside the Gaussian surface, the charge is equal to 0. See, charge is almost outside, not inside. Now we know that the formula that is equal to Gauss formula, that is phi is equal to integration E dot ds. This is equal to charge enclosed by epsilon naught. Now if E into integration of ds is equal to charge enclosed is 0 by epsilon naught, so what will happen about electric field? So electric field will be equal to 0 by epsilon naught into ds. So finally this will be electric field will be equal to 0. I hope you have understood now. Okay. Now see here, same thing I have already written. Now fifth one is the electric field at a point P, which is at a distance of r from the infinite plate sheet. Plate sheets are infinite. We don't know where it is extended, but I want to know that electric field at a point. Let us consider electric field at a point, this point, right? So this is the point P, which is at a distance of r only. So can we make the Gaussian surface like this? See here. See, earlier this plate was like this. See, try to understand here. This plate was like this, right? And this plate has a charges, and it has a charge density. It has charge density sigma is equal to q by a, right? So or we can say charge is equal to sigma into A. But we know about the charge density, that is sigma, right? We want to find a electric field at a point P. So let us consider a distance of this point P is R. Can we make a Gaussian surface like this, which will pass through the point P and it will create like this? Okay, this is also at a distance R, and this is at a distance R, right? So this what I have done. Now if we have drawn the Gaussian surface, what we have to do? We have to find the electric flux as each surface. So first of all, see how many surfaces are there. One surface, second surface, and this is your third surface. Third surface is the curved surface. Now by Gauss theorem, E dot ds is equal to charge enclosed by epsilon naught. So for first surface, E dot ds plus second surface, E dot ds, third surface, E dot ds. And this is equal to charge enclosed by epsilon naught. Now charge is equal to sigma into A, right? Now tell me which part you will take. See the direction of electric field. See here. Here direction of electric field and area vector are same, so theta is equal to 0 for case 2. Here also theta is equal to 0 for case 1. But here if we talk about any surface on the curved surface, so the direction of the area is this and the direction of electric field is this, so the total angle is 90 degree. Now for one surface it is 0 degree, second surface it is 2, and third surface it is 90 degree. Now if we break this, see here, this will become 0. Why? Because the angle theta is equal to 90 degree. So we will have a E dot ds. Now if you see properly that this both surface are same, having same area, so surface 1 and 2 both are same, so why don't we add like this E dot ea, and this is equal to charge enclosed by epsilon naught, right? So how many ea are there? 2 ea. So 2 ea is equal to charge enclosed. So charge enclosed, we have already told that charge enclosed by this formula we have got charge enclosed is equal to sigma into A. So we can multiply it by sigma into A and divide it by epsilon naught. So finally our answer will be electric field is equal to sigma by 2 epsilon naught for charge due to infinite plate sheet, right? So I hope you have understood this point. Okay. So I may hope that electric field is now complete. Gauss law is complete, but now let us, dear student, we need to discuss about electric field due to dipole. You know dipole means what? Again, I am telling you, dipole means two-fold. See here, let us consider there is a charge plus q and there is a charge minus q, and it is separated by a distance 2a. Then this whole combine is known as dipole. It is known as dipole. Okay. So we want to find electric field due to dipole. Why we want to find electric field due to dipole? Because if there is a combination of two charges and we want to find electric field at this point, electric field at this point, electric field at this point, so how you will find this? Okay. So I will discuss one of the case on an axial line. So this is very important. There is one case that is axial line. What is axial line? See, suppose there is a charge q minus q and plus q. It is a dipole having a length of 2a and the center of the dipole is O. Now at a point P, which is at a distance of r from the center of the dipole. See, whenever you want to find a dipole, whenever you want to find the position of any object or any place from the dipole, means you have to take the center. If you are here, so you have to take this position. If you are here, you have to take from center only. If you are here, you have to take center from only. If you are here, you have to take center from only. So we are considering this distance as a r. Now, basic formula you should always remember that electric field is equal to kq by r square. Okay. Now, first of all, you tell me, electric field at a point P due to positive charge, that is this charge, will be how much? So can you tell me the distance, this distance? So this distance, this is your what? See, this is your A, this is your R. So this distance will be R minus A, right? Again, if you want to find this distance, so this is 2A, see, this is A and this is R. So total distance is R plus A. So we want to find electric field at a point P due to charge plus Q. So this is plus Q. So KQ by R minus A whole square. And if I want to find electric field at a point P due to negative charge, that is E minus Q, that is equal to KQ by R plus A whole square. Okay. So we have got this. Got it? Now we want to find net electric field at a point P due to plus Q. So total electric field at a point C. See here, let us see here, this is a charge plus, this is a charge minus Q, this is a charge plus Q, and this is the point P. So the electric field due to plus Q charge will be like this, and the minus Q will be little bit small. So net charge will be what? Net electric field will be what? E due to plus Q minus E due to minus Q, because it is in this direction. So we can now calculate here E plus Q minus Q. Now KQ by R minus A whole square. So we have put here KQ by R plus A whole square. So when we calculate it, see, very important, KQ you take common, 1 by R minus A whole square minus 1 by R plus A whole square. Now you need to calculate. When we calculate, so this basic things you know that how to calculate it. So I don't want to waste that time. So this will be K is equal KQ into 4RA by R square minus A square. So finally we are getting 2KQ KR into 2A cube by R minus A square. Okay. Now you know that 2AQ is what? Dipole moment. And this dipole moment into 2K KR, 2K into R, right? So here let us see here. Dipole moment. So electric field here we are getting as 2K P into R by R square minus A square whole square. Now, if A is very small, then what we can do? It can be 0. So what you will get? Electric field E is equal to 2K P into R by R to the power 4. So this will get cube. So finally, your answer electric field will be E is equal to 2K into dipole moment by R cube. And you know one thing I have missed here. So direction of a dipole. What will be the direction of dipole? So here direction of the dipole is from this. I will use another ink so that you can find out. See, direction of dipole is in this direction. So this is dipole direction. And it will always be from negative to positive, not positive to negative. Positive to negative, there is a direction from electric field, but for dipole, it is just opposite. Now you can, I hope you have understood this. So the dipole direction will be in this direction. So finally, if you want to find electric field at this, see, finally you will get the direction. So the electric field at this direction will be in this direction only. That is dipole direction. Dipole direction, right? So I hope you have understood this. I hope you have already understood this. Now let us discuss another case that is very important. That is electric field due to a dipole on an equatorial plane. What is equatorial plane? Let us construct this. This is a dipole, and the plane passing through the center of the dipole. Let us consider a plane which is passing through the center of the dipole. See here, this is the equatorial plane. See, because this is passing through the center of the pole. Now I want to find electric field at any equatorial plane. So it may be here, 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 it may be here. We don't know. But we want to find at a point P, we want to find an electric field. Now let us go here. Now let us see here. This was the negative charge, this was the positive charge, and this both has created a dipole, and the distance between these two both is 2a. Right? Now the angle is theta and an angle is theta. Now let us don't discuss about angle. Before that, we need to find where to find electric field. So I want this at this point an electric field. So we have just imagined a triangle shape like this, and the angle is theta. Now the electric field due to positive charge will be in this direction, and electric field due to this negative charge will be in this direction, right? Now the distance between these 2 points is root under r square plus a square, because this one is length is a and this one length is r. So by Pythagoras theorem, r square plus a square root under. Okay. Now same length here also. Now we have to find electric field due to positive charge. So due to positive charge, k cube by r square plus a square. Electric field due to negative charge is equal to k cube by r square minus a square, r square plus a square, because both are at the same distance from the charges. Now the thing is that one electric field you are getting in this direction and another in this direction. Now we have to take a horizontal line. So can we tell that this is angle theta because this is angle theta? We can also say this is an angle theta. This is alternate angle, and it is dividing, theta is dividing in two equal part. Or you can say this is our, and this is this angle, both are alternate angle, right? So we have understood now how to give a value of a theta. Now you have understood, and you have understood how to write this. Now E plus Q has two components. The one component is E plus Q cos sin theta, and another is cos theta. E minus Q has also one E minus Q cos theta, sorry, sin theta, and this is cos theta. See, both are equal and opposite, equal and opposite. So what they will do? They will cancel each other. So what constitute the net electric field? These two one, because they both have a same direction. Why I am cancelling here? Because the magnitude of E plus Q and E minus Q's are same. See here, K Q by R A square plus A square. Here also E minus Q as a K Q by R square plus A square. Since both are equal but opposite in direction, that's why it has been cancelled out. This component, vertical component, has been cancelled out, but horizontal component is not yet cancelled out, right? So vertical component of E plus Q and E minus Q will be cancel each other, and horizontal component will be added. So the net electric field will be 2 into horizontal component. So the net electric field P is at a P is equal to E plus Q cos theta minus Q cos theta, but the both have a same magnitude, so we can twice it. So we have done this, right? So finally we know that cos theta is equal to what? See here from figure, This is angle theta. This is r. This is root under, this is c. This is the root under ra square. R square plus a square. This is r. This is your a. So cos theta is equal to base by hypotenuse. So base is your a by r square plus a square root under. So we can put the value same as cos theta is equal to a by r square plus a square root under. Now when we put here, so we can combine it to a qk r square plus a square 3 by 2. Now 2aq is, we have already known, this is your dipole moment. So this is kp into ra square plus a square 3 by 2. Now if a is very small, then what will happen? We can ignore this a, so we will get kp by r cube. And in vector form, it is minus kp by r cube. Now you surprised to know that why I have kept here minus kp, minus kp. Now let it see the direction. Direction of the dipole moment. First of all, tell me what is the direction of the dipole moment. See, direction of dipole moment P will be in this direction, that is from negative to positive. So here also direction of dipole moment will be negative to positive in this direction, but the electric field is in this direction. So both are in opposite direction. That's why we have to put negative sign so that we can justify it, right? So I hope you have understood now it, right? One thing you have noticed here, that axial we have 2 kp. For axial, electric field due to at an axial point is equal to 2 kp by r cube, but at equatorial plane it is kp by r cube. It means that we can find a relation, that is e axial is equal to 2 of e twice the e equatorial. Okay, so axial there is more electric field rather than equatorial. So I hope you have understood all the whole chapter, that is electric field chapter. You have understood electric field, right? Electric field you have already done. So 3 parts I have made, and whatever you are getting a doubt, so go through all 3 videos so that you can understand well. And if you have a doubt, you can comment in the comment section below. And one thing you should understand, that you must subscribe. Why? Because I am going to make a series of the videos here, and I'm also going to make a live classes on the previous year questions. So be updated soon. I will meet you again. Thank you for watching my video. Thanks a lot.